have another panelist, Professor Xiaonan Wang, joining us remotely from China. So Xiaonan, thank you for making it available. I know it's getting late in China, and also thank you for making it available during your another AI workshop. So feel free to share anything you learned. So the floor is yours.
So hello everyone. I'm so sorry for a technical issue. I wish I could be there, but we are hosting another AI for Materials Discovery conference in Shanghai, China. I definitely hope that I can invite you to visit us in China someday. Now the trip is quite smooth, so we hope that the communication is back to normal very soon, at least in the scientific world. Because I come from the chemical engineering background in system engineering, just like many of you in system technology research. So I want to share some of our recent work on the multi-scale discovery for the sustainable chemical and the catalysis design. So we have really different spatial and temporal scale from the atom molecules, catalysis, membrane technologies towards the carbon neutrality target. Right. So we have these different technologies linked together. I will skip the background, but definitely we have heard so much good work on the computational prediction, the inverse design, and how could bridge the computing, simulation, and experiments is our recent target that we really hope to show several of our trials to bridge the computing results and the experiment in even the industrial applications of the catalysis discovery, and eventually to have new principles discovered. So in our previous work, we also showed a lot of materials design to show how we can incorporate machine learning simulation to guide the materials design, and also this integrated workflow to either have AI ML in the loop, or now we say have human in the loop of machine learning, but eventually we hope to co-work together to discover the knowledge beyond the current scope. And for the topic of heterogeneous catalysis, recently we really look at how we can approach it through the multi-scale from the micro level to look at its intrinsic activity to model it. So I will introduce briefly the recent work we did on the surface energy prediction and also the particle level to synthesize the exact particles and eventually in chemical engineering to use that in potential industry reactors. So we have this kind of it's very similar to the previous speakers showing how we can use automation to get the designed recipes and synthesis conditions implemented. So in one case of the atomic design of this semi-heterogeneation catalysis, similar approach before we got the descriptor and we conducted active learning guided design to use computational DFT models to see what's a biased bimetal catalyst for this heterogeneation catalysis. So in this case, we identified several of the biased combinations, like this kind of NILN-based materials for the catalytic conversion, the ethylene to ethane with a very good selectivity and overall yield more than 97%. And interesting in this work, we realized it takes a lot of time to calculate the surface exposure. And then we started a project to screen this whole database to see if we can screen all the candidates catalysis, especially bimetal, trimetal, to look at the surface energy to generate a model that can have this crystal nanoparticle surface energy prediction. So by using this, we hope to build up a comprehensive data set. And definitely active learning could be the good tool to guide the search of the data set. So we use AI to see how we can screen the whole bimetal region and have the calculation combined with that to calculate all the metal elements with the metal surfaces with all this data accumulated. And then with the data, we train these machine learning models. Interesting, just now in Zachary's talk, we see the involvement of the model structure. Definitely this year, Equiformer V2 overperformed all the previous models. Similar in our case, we eventually use this backbone structure, and based on the model, we get this model prediction of the machine learning. It's kind of a machine learning force field model, and based on this model, we thought it's quite nicely pre-trained model. So we submitted to a computing journal, and then editor asked us to add the experimental validation. We found it very interesting that now we need to bridge all the simulation and experiments. So we use these large language models, LLM tools nowadays give us a very good strength that we can screen all the published data. So we decide screen all the Nature Science JAX papers to search for the keywords and decide relevance first, and then we extract the information to compare the XRD experimental data and also TM this data to validate if the exposure of the surface is correct. And then using this extract information, we collected a whole experimental data set. And also we conducted several experiments to get the own data set to do the valve shape prediction and found a quite good accuracy, more than 75%. So this is one trial that we did, trying to use the pre-trained model to predict the surface exposure and then the synthesizability of these crystal, of these particles. So based on this case, we hope to publish a data set and then trying to have more pre-trained model really to bring a lot of acceleration in this field. Beyond this, at this micro level, we also conducted a lot at process level. So previously, we used the large language models to search the whole literature and get kind of the predefined search space. Based on this search space, in this case, we try to do ammonia synthesis in the future green hydrogen background. And also this using the kind of automated equipment, we can start from this IM generated feasible region and use this active learning guided search to get the proper structure of the catalyst. But not just structure, but more importantly, we can use this online optimization with the self-driving reactors. It's not like the self-driving laboratory, but just the fully automated, inherently safely equipment for the synthesis conditions optimization. So it's turned to be quite effective in many of the industry catalysts. And beyond that, we also hope that to put the catalyst particle in the reactor scale. This is very chemical engineering. We found this kind of the principles of transport and the reactions, and use this knowledge to form this neural ODE and use neural networks from this neural ODE framework to match this real reaction data into our ODE framework so that we can have kind of digital twin from this micro atomic scale towards the particle and eventually at the reactor scale to have this multi-scale scale up. And interestingly, we did some industrial catalysis tests and found this way quite useful to guide the industry. Now a lot of companies are purchasing this kind of unchained system or ChemSpeed to have a lot of this capability of get experimental data. So we use this active learning guided search and eventually to get several this one for it's one actually it's not heterogeneous, but it's a good demonstration of how they can use this framework workflow of designing the catalyst for the new type of catalyst that have better activity than the commercial, even than the commercial ones. Again, that's just some basic recent cases that we have conducted and the envision into a future. Definitely the AI labs is quite common nowadays, and also the AI lab towards the AI industry to scale up this kind of catalytic performance to the green future is our goal. With that, I want to acknowledge all our team members, international collaborators, and funding support. So sorry for the technical issue. I hope to discuss more with you during the panel discussion.